Dr. David Grabiner from CCR and the National Security Agency, who will speak about more probabilistic proofs of group length formulas involving trees. We're going to take David out to the Evelyn restaurant on 145 Eastern Avenue. You're all welcome to join us, but please let me know immediately after the talk, David.
Okay, so this is joint work with Mark Tiefenbrook at University of California, San Diego. And I'd like to begin by thanking you for the opportunity to speak at this seminar. So first, let me motivate the term hook length and why this type of problem is of interest. I'm not going to prove this result, but I'll explain where the term hook length comes from. So this is motivated by a problem in the enumeration of Young tableau. In the Young diagram of partition, we say that every cell has a hook. So this cell has, the hook contains the cells to the right and below, and this cell itself. And the length is the total number of cells. So we say this cell has hook length 4. A standard Young tableau is a filling of the diagram of the partition with the numbers 1 through n, so that all the rows and columns are increasing. And the classical hook length formula tells you how many standard Young tableau there are. This is important in things like the representation theory of the symmetric group. It's n factorial divided by the product of the hook lengths. And this is normally proved algebraically, but since the lengths of the hooks appear in the denominator, you might guess that this could be turned into a probabilistic proof, that you make some choice out of hij possibilities for each of the cells and use that to generate a random Young tableau. And that has been done. I'm not proving it here, but this is done by Neinhuis and Wolf. So now with that,
I have a trivia question for you. Who gave a beautiful combinatorial, direct combinatorial proof of this hook length formula? Not probabilistic, but purely bijective. Who was the first person to give a purely bijective proof of this?
I'm not familiar with it.
Oh, okay. Myself.
You? No.
Yeah.
Okay, I'm not.
Together with Deborah and Debbie Franzbach in 1982.
Okay, so now in a tree, we define an analogous hook length formula, and we call the things hooks even though they're not necessarily hook shaped any longer, but to get a similar formula. In a rooted tree, we define the hook of a vertex to be the set of all the descendants of that vertex, including the vertex itself. And the hook length, again, is the number of vertices in the hook. So here's a tree with 6 vertices, and the root, therefore, has hook length 6. This vertex has 2 descendants plus itself, so its hook length is 3. A rooted tree has an increasing labeling if the numbers 1 through n are placed in the tree, and every vertex has a lower number than the label of its children. And now we have an analogous hook length formula for any rooted tree with n vertices. The number of increasing labelings is n factorial divided by the product of the hook lengths. This theorem is well known, and it's been proved probabilistically. It appears in Knuth, for example, and it's been proved probabilistically before. Bruce, Sagan, Young, Nanier have a probabilistic proof. So notice the motivation. This formula really has the same form as the enumeration of Young tableau of a given shape. The only difference is in the definition of a hook. So although that hook length formula for trees is known, I'm going to present a new probabilistic proof of it because this proof really motivates our own arguments for the formulas that will be the main results here. So choose a random labeling of a tree with labels from a set S as follows. Give the root a random label. Then if the root has children v1 through vk, partition the remaining labels randomly into subsets of size hv1 to hvk. That is the appropriate number of labels for each of the subsets. And apply the algorithm recursively to the hook of each one of the children with that subset. So here's an example, and this is a tree in which it happens that our random labeling does give an increasingly labeled tree. We have 6 vertices, we have 6 choices for what to give the root. I picked 1 for the root, and then I chose randomly to put 3, 5, 6 in the left subtree and 2, 4 in the right subtree. Okay, now I go after the 3, 5, 6 branch, and I chose to make 3 the root, and 6 and 5 for the left and right subtrees, which since they're leaves, there's nothing more to do. Now I go after 2, 4, and I have, again, a random choice. So the probability was 1 over 6 times 3.
Oh, God, I'm sorry. I'm sorry.
Probability was 1 over 6 times 3 times 2 that we get an increasing labeling of the tree. Because we had 6 choices, and 3 choices, and 2 choices for which label to assign. So our algorithm gives a uniform distribution on all the labelings because we assigned a random label from all labels available to the root. And then we randomly partition the remaining labels. For every vertex, the probability that the vertex was assigned the lowest label in its hook is 1 over the hook length. So the probability that we get an increasing labeling, assigning a label to every vertex, is 1 over the product of the hook lengths.
So how is it different than the original proof?
The original proof did was it constructed an increasing labeling. What I'm doing here is I'm constructing a labeling, which I know I can do with probability. We construct an increasing labeling and then show the probability you get labeling make these probabilities right. Here I'm constructing any labeling, which has probability 1, and the probability the labeling comes out to be increasing is the desired probability. So that's the essential. That is the essential difference. Okay, so for our main results, I will state the results in a minute. Hand proved 2 different hook length formulas for sums taken over all the binary trees, in which the hook lengths appeared in the denominators, but not just as 1 over HV as they did in the formula we just had, and also in many other hook length formulas for Young tableau and such, but also the hook lengths appeared as an exponent, 2 to the HV minus 1.
By the way, so before also the trees were binary?
No, my previous example just happened to be binary. That wasn't essential. Hand's results are specific to binary trees. And then they've been generalized to other types of trees as well. So Yang proved a generalization of Hand's formula to a weighted sum over all ordered trees. And with her weights, she had a factor of 1 over HV m to the HV minus 1. Both of these formulas, just by their form, suggest there should be a probabilistic proof. And in fact, there is one. A year ago, Bruce Sagan presented probabilistic proofs of Hand's first formula and of Yang's generalization at this seminar. And he actually credited us. And the proof he presented was not quite the one that I'll present here. And he conjectured that Hand's second formula had a probabilistic proof as well, and then credited us with proving that. And he said that our proof was better because our proof could prove Hand's second formula and his couldn't. And we will return the favor because we will present his original proof and show that in fact his original proof does prove Hand's second formula, as does ours, with only minor modifications to both. But what I particularly like about our proofs is that they give an intuitive explanation, the way a probabilistic proof should, of why these things are true. Each of these probabilities is used directly. For every vertex, we make an HV-way choice, and then we make HV minus 1 2-way or M-way choices to get our probability and build a random labeled tree. So both arguments are ways of getting a tree. Sagan's argument builds the tree in numerical order. You place label 1, then you place 2 somewhere, then 3. We'll construct the tree recursively. Our process is analogous to depth-first search. We construct the tree, then we construct the subtree for the root, then we construct the subtree for the leftmost descendant, then for the second descendant, then for the third, if there are 3 descendants of the root.
So is it analogous or is it exactly depth-first search?
What's the question?
Is it exactly depth-first search?
Well, it's analogous in that the way we build the tree, we build down the leftmost subtree. We're not actually doing a search at all, but it's the way we build the tree. Yeah, yeah. And then the second formula will prove both ways using a minor variation of our algorithm and of Sagan's. So in order to state the formula, let me clarify a definition. We define a binary or m-ary tree to be a tree in which every vertex has 2 or m ordered slots for children, and the slots may be occupied or vacant. So here are the 5 binary trees on 3 vertices. 4 of these look like they're isomorphic, but going left, left, and left, right, and right, left, and right, right, I will consider those 4 trees to be distinct for these purposes. So here's Hand's formula, and I'm going to place this on the board so that we have it for reference. The sum over all binary trees, product over all vertices in the tree, 1 over HV2 to the HV minus 1 is equal to 1 over n factorial.
There's nothing more general if you replace 2 by x?
Yes, there is. There is, and that's Yang's, that is corollary to Yang's generalization.
Okay.
This is the form in which Han originally stated the result, and therefore I'm stating it this way first.
Okay.
So this is the formula for binary trees.
So, you binary trees are not complete binary trees?
No, and again, Han's second formula, which I'll get to later, deals with complete binary trees. So, because I'm going to be referring to this formula and its generalizations repeatedly, I want to leave it on the board.
Yeah, but, so remind me, binary trees, you can have...
So these are the binary trees on...
1 or 2.
So you can have either 1 children?
You can have a left or a right or neither or both.
Oh yeah, okay.
And having a left child only and having a right child only are distinct.
It's also Catalan? It's 5 because Catalan number? Is it Catalan numbers? So, in general?
Are these numbers the Catalan numbers?
Yeah, I think so.
Okay.
The middle line, this is good.
So then, it's in by
Yeah.
section. Oh yeah, you can probably complete this.
Because they have satisfied the recursion for the Catalan numbers.
Yeah,
because if you have a binary tree on n vertices, then you have k vertices in the left subtree and n minus k minus 1 in the right subtree.
Yeah.
So yeah, so the number of binary trees is the Catalan numbers. Okay, so Han proved this result by induction, and Sagan gave a probabilistic proof, and also just last week, this didn't make it into the slides, it just appeared on the archive. Chen, Gao, and Guo have a combinatorial proof of Han's formula and of these generalizations using staircase labels attached to the trees. So a very different method from either of ours. To prove the generalization, first let me state it in the form that Yang first actually stated it. So we define an ordered tree to be a rooted tree in which an order is assigned to the children of each vertex. Fix the value of m. Yang assigns a weight of the tree to be a product of the weight of the individual vertices, and each individual vertex has weight m choose CV, where if the vertex has CV children. If m is an integer, this weight is the number of ways to make the tree T into an m-ary tree, preserving the order of the children at each vertex. Sagan in his paper mentioned this only for m equals 2, but it works just as easily for any m. So here's an example of a tree with 4 vertices, which has weight m times m choose 2. There are m ways to decide which one of the m slots this child goes to, and m choose 2 ways to decide which 2 slots these go to, keeping the order. So for example, there are 2, which is 2 times 2 choose 2 ways to make this tree into a binary tree. So here's Yang's formula as she originally stated it. The sum over all trees, over all ordered trees on m vertices, of the weight times the product of the hook length times, times product 1 over the hook length times m to the HV minus 1 is equal to 1 over n factorial. And Sagan's probabilistic proof originally was for the formula in this form. But it works more naturally to actually make the ordered tree into an m-ary tree and generalize this to m-ary trees. Now, Hand's theorem is the m equals 2 case. For all positive n and m, summing over all m-ary trees, we get the sum over all t, the product over all vertices, hv to the m hv minus 1 is 1 over n factorial. So let me now just update the formula to give the generalization. So this is the corollary to Yang's result, and we'll see that in both our argument and Sagan's, the proofs are exactly the same. So now that we've stated that, here's how we'll prove the algorithm. And here's how we'll prove it probabilistically. We'll choose a random labeled m-ary tree, given a set of labels. Assign a random label to the root. Partition the remaining labels into m subsets which may be empty, S1 through Sm. So this is the difference between the algorithm here and the algorithm for finding a random labeling of a known tree. Since the tree isn't known, we don't have any constraints on the size of the subsets. But otherwise, the algorithm is the same. Now, if a set isn't empty, put a child in that subset, put a child in that set, not yet labeled which is not yet a labeled vertex, and apply the algorithm recursively to that subtree to construct a subtree rooted there with vertices labeled by the SI. So this is what I mean by analogous to a depth-first search. I take the root, then I construct its leftmost subtree, then its second subtree, then its third subtree, and the way I construct the first subtree is by constructing its leftmost subtree, then its second subtree, then its third subtree. So here's an example. I will construct a random tree. This one will be binary on 6 vertices. So I have 6 choices for the label to label the root. And I picked 3 as label for the root. And 1, 2, 6, and 4, 5 was the partition. So note that I had 6 choices for the root label, and then 2 to the 5th choices for labeling the 5, for where I put the 5 descendants. Now I go to the 1, 2, 6. And I picked 2 for the root of that subtree, which was 3 choices. And I had 2 squared choices for where I put the 1 and the 6. They happened to be on separate sides, but they could have wound up on the same side. Similarly here, I had 2 choices for the 4 and the 5. And the 4 could have been either the left or the right subtree, and I chose randomly to make it a right subtree, and also so that it would fit on the screen. And then not overlap the 6. And this is essentially a proof. I can make it formal now. We can get any, with the starting set of size n, we can get any labeling of any m-ary tree on n vertices because we can have any partition of any size. Now, for every vertex, we had HV choices for the label when we made that vertex the root, and each of the remaining labels, HV minus 1 of them, could have gone to any of the m subtrees. So that says the probability we get a particular tree and a particular labeling of that tree is the product of 1 over HV to the m, times m to the HV minus 1 over all the vertices. Now sum that over all the labelings of all the m-ary trees, and we get n factorial times the sum is equal to 1, the probability we get some tree. And that is exactly Yang's formula here, multiplied by constant n factorial. There's no reason in this formula that m has to be constant. And in fact, Sagan generalized his result to a place where m varies with the position of the vertex v in the tree. It's a little harder to understand the theorem here, but the proof doesn't change at all. We take an infinite tree, t bar, in which a vertex at position v has m sub v possible slots for children instead of a constant m, and take a sum over all subtrees t of t bar. Same formula, the sum over all trees that are a subset of t bar, the product of all the vertices, 1 over hv mv to the hv minus 1, is 1 over n factorial. And the algorithm and proof are exactly the same.
But this is cheating. It probably you had the proof. He had the proof, and then he looked how he can generalize it.
Yeah. That's. I think that's the way this happened. That he proved Yang. Although he had not proved Yang's result in this form. He proved Yang's result with Yang's original weights, and then got this generalization, which does prove.
So he looked at your proof.
No, he had not seen our proof. This predates our paper. This predates our paper. This was already in his paper, which was published before we did our work.
So you had that proof of Yang's?
Yes, he proved Yang's.
Yeah.
Yeah.
So
he didn't. It's hands.
So he started to follow from his proof, from the method of proof.
This proof is this is in his paper, and it's also in ours, because the proof is exactly the same. It's just we use m sub v instead of m.
Yeah.
Hans and Yang's formulas are the cases in which T bar, this is an infinite binary or an infinite m-ary tree. But here's an example of another case where Sagan's generalization might be used.
Can I ask you a question?
Yes?
What is this position of a vertex in this context?
Position.
Could you come back to the previous?
Yeah, okay, yeah, that's what I'm giving here. That's what I mean by here. That here in this tree, this is an infinite tree. The root has, in this particular tree, the number of children allowed for a vertex, that is the number of children the vertex has in the infinite tree, is one more than the depth. So here's an example of an infinite tree in which the root has only one child. This node at depth 2 has 3 children. And the red tree is a specific subtree with 6 vertices of this infinite tree. So the m sub v is the number of vertices in the infinite tree. So in the infinite tree, this vertex has 3 children, and then I happen to have chosen a subtree in which it has none.